Hi, and welcome to IV Tutor. My name is Edmund, and we are looking at the last and final type of questions that you get on the Big O. And these questions are based on inference, which means you are given the graph of an algorithm, and based on that, you are supposed to determine what the Big O should be, right? So this question is a two-part question. So the first question, they say focus on algorithm A, and then the second question, they say focus on algorithm B, but same thing. And what they're doing in this case is they are saying, now, given these values of n, this is the result of your algorithm. So if n is 4, then it's 16. If n is 8, then you get 256. If n is 16, then you get 65536. So what is the runtime complexity of algorithm A based on this? Well, ignore B for this question. It's a two-part question. We're focusing on A right now. Sometimes you can try to just infer based on how these values are growing in respect to how your values of n are growing. And based on that, you can then say, this looks like 2 to the power n, because definitely it cannot be log n, because log n is the slowest, right? And you look, n is 4, you get 16, n doubles, and now you're in 256, and then n doubles again, now you're on 65536. I mean, it's crazy. So you can just by, look by inspection, confirm that it's not log n, it's not n, because n would be linear. It's 16, then it should be 32 here, and then it should be 64 here. And you can sort of say it's not squared, because 8 squared is 64. 16 squared is not this big number here. It's more like, you're 128, 256 there. So you can sort of end up saying, yeah, this should be 2 to the power n, but just by looking at how your values are growing. The best way to confirm is to actually find the expression that maps your n to your value. Like, what is it that we have to do to n to end up with 16? What is it we do to n to end up with 256? What is it that we do to n to end up with this number? So that way, that approach is not straightforward, because you don't really know. It can take a while for you to figure out that exact expression. So you always have to strike a balance between, inspection, is it making sense? Or do you have to really find the expression? For example, in this case, I would try, 4 and 16, I would say 4 squared is 16. That looks right, but let's see if that works for here. 8 squared is 8 squared 256. No, 8 squared is 64. Okay. And is 16 squared this guy? Not really. So what is mapping n to 16? So now you have to sort of try out a few things and try and think okay, what is it that we can do to 8 in order to get 256? For example, if I go, the log of n is 2, because now if we're operating in base 2, that means the log of 4 here is 2, the log of 8 here is 3, the log of 16 is 5, right? So what is it that we can do, to n to get 16? So this one is not really helping. Let me focus on this one. So we've got log n is 3, so 8 to the power 3. So is it 8n to the power log n? Yeah. Then 16 to the power 5 is not this one. So okay, what is it? Okay, now, so you have to try a whole different permutations until you can figure out what is mapping your n to this. Okay. All right. So in this case, we can then also try and do, okay, what is 2 to the power 4? That's 16. Okay, 2 to the power 8. That's 256. 2 to the power 16. That's that guy. Oh, okay. So that's it. So in this case, our algorithm is simply 2 to the power n, and therefore our big O becomes 3. So sometimes you can also play around with the answers and try and see what can you do to get this number from n. So it's trial and error sometimes until you get it right. So in this case, it's a direct mapping. 2 to the power 4 is 16. 2 to the power 8 is 256. 2 to the power 16, definitely that guy. Okay, let's look at algorithm B, right? So now let's do the same question. When n is 4, we get 6. When n is 8, we get 11. When n is 16, we get 20. It's not a constant, because definitely these values are changing for increasing values of n. Therefore, the size is contributing in this case. What can it be? What can we do to get 6 from 4? What can we do to get 8 from 11? You know, I know that the log of 4 is 2. Therefore, if I add 4, I get 6. That makes sense. So here I'm saying if I go log n plus n, I'm getting 6 because log 4, 2 plus 4, 6. Let's try that out here. Log n, that's log 8, that will be 3 in base 8. So I'm saying if 2 to the power 3 is equals 8, then log 8 is obviously equal to 3, applying in base 2. So log 8 is equal to 3 plus 8, 11, that works. And log 16 is 5 plus log 16 is 4 plus plus n, 20. Yeah, that's it. So here I would say it's log n plus n. Take the highest power and we end up with 2, which is n. So the best way is to try and find the expression which maps your n to your value. So these questions are very tricky because it's like, what formula are you using? There's no formula. I'm just looking at the value of n, looking at the result or the value of the algorithm, and then trying and find that relationship. Then from there, I can then say, oh, that's the expression. Therefore, this is the answer. So in this case, because it's log n plus n, you'd go with n, which is the highest power. Therefore, your answer would be 2. Let's look at a different example here. When n is 2, I get 2. This one here, let's look at this one. When n is 8, I get 24. Okay, and when n is 32, I get 160. Okay, I'm looking at the answers here. There's like n squared. How can I get 24 from 8? Because I know that log 8 is 3, and 3 times 8 is 24. So I'm going maybe n, log n. Let's try that here. So 2 log 2. Log 2 would be 1, so that's fine, it works. 8 times log times 3, that would be 24, that's fine. And 32, that's 5. Times 32, that's 160, yeah. Therefore, it's n log n, and therefore I've got my answer. There, 4. Right, let's look at the part B of the question. When n is 2, I get 2. This one is not helping. Let's look at n is 8, I get 64. N squared is 64. So I'm going here, maybe it's n squared. Right? So 8 times 8, 64. 32 times 32, here I get 1024. I can guess they wanted 4 here, not 2 there, because definitely this is n squared. Right, let's look at the last one. This was a 3-part question. So I've just extracted these 3 algorithms, and we'll try and work out the expressions for each. And after some thinking there, the first one looks like it's n squared over 10,000 multiplied by 4. You can just plug in. So if you've got 100, that means it's it becomes 10,000 over 10,000 multiplied by 4, which gives you 4. For 1,000 there, it becomes 1,000,000 over 10,000 there, which gives you times 4, which gives you 400. And then the last one, which is 10,000 squared obviously over 10,000, just becomes, this gives you 40,000. So it does look like n squared over 1,000 multiplied by 4, which then obviously gives you n squared is your big O. Let's look at the second one in blue. This one is quite easy. It looks like this one would be n over 100 multiplied by 9. So there, 900 over 100 times 9 equals 9. This one would give you 90, this one would give you 100, which means this would be n over 100 times 9, which means this gives you n as your big O. Then the last one, this one in red, we've got 21. This looks like it's n log n plus 1. So log n, that's 2 times, not n log n, sorry. We want to get 21 from from n, that will be 10 log n. So this looks like it's 10 log n plus 1. So 10 times 20 times 2, that's 21, plus 1, that's 21. That gives you 21. Log 1,000 is 3 times 10, that's 30, then plus 1, 1. And then 4 times 10, that's 40, plus 1, 41. So this would be 10 log n plus 1, which means this then becomes log n. So that is basically what the big O's for these three algorithms would be. But like I said, it takes a bit of time to try and to find the expression which maps your n to your big O. So either if it's taking too long to find that answer, you can just try and infer or guess from the values that you're looking at, because that will be your best chance of getting the value right. So based on this, we can then summarize and say this here is n squared, this is n, this is log n, right? So you can just rewind and see how we did it. But basically, this is the last step of the big O questions. This I don't like a lot because there's just no much logic to it. You just have to try and find the expression which maps your n to your result or to your algorithm. And based on that, you can be very confident as to what your big O can be. The other way is just by inference, which means you can look at how your n is growing and how your values are growing, and then check if it can be n or n squared or log n, just based on the growth rate. That is also another way you can do it. But to be very 100% sure, you have to find the expression. Okay, so that's it for these algorithms. I'm just going to summarize. We said for algorithm A, the actual expression is n squared over 10,000. Or over n to the power 4, over 10 to the power 4, multiplied by 4. For algorithm B, we said it's n over 10 squared multiplied by 9. For algorithm C, we said it's 10 log n plus 1. So if you plug that into these algorithms, you can see that it gives you the resulting value in your algorithm. That's the big O for you. Just needs a lot of practice, especially the first part of the big O, which we covered in the first video, and the second part, which we covered in the second video, which is the calculations. Those are the most common types of questions you see in exams. And these ones that we were covering here are very popular in assignments. But basically, this sums up the big O discussion. I'll see you again in other topics. Cheers.